Post-tensioned, ground-supported industrial slabs. What will be your takeaway from this presentation? First, what are the ground-supported slabs? What types there are? Why are they post-tensioned? How are they designed? And how are they constructed? And we go through a design example. The different types of ground-supported slabs, the three types are mat or raft foundation, SOG, which is slab on ground on expansive soil, industrial slabs. The focus of this presentation is industrial slabs, but first a short introduction of the other two. The mat or raft foundation is where the load from column and walls in a high-rise has to be distributed widely over a large area of low allowable bearing pressure. In this case, post-tensioning can help. Look at the profile of the tendon. It is profiled such as to lift the weight from above here and bring and dump it away somewhere in the span. So the profiling of the tendon will help to redistribute the applied load and result in a more uniform distribution. Here is an example view of a raft foundation. Observe that below the column the tendons are low, and at midspan between the columns the tendon is high, so it can push down the load picked from the two sides. The other type is slab on expansive soil, where volume of soil changes seasonally due to variations in moisture, such as summer and winter, and the soil content has enough substance, clay type, that will expand and shrink depending on its moisture content. For low-rise buildings, the perimeter of the structure is subject to changes in moisture over different seasons. This up and down movement will damage the building above unless provisions are otherwise provided. The image on the left shows a typical construction of a ground-supported slab on expansive soil. Type 3, which is subject of this presentation, is where you have an industrial application and the client wants to have a smooth surface, level surface, crack-free surface, and a strong surface so that the forklift can operate well, raise the load without becoming out of plumb and likelihood of toppling. The example on the left is an industrial building finished in Brazil with ground-supported industrial post-tension slab, and the image on the right shows such a construction ready to receive concrete. It's all detailed and ready. Now, what are the performance requirements of industrial slabs? You want a smooth and level surface, no cracking, no joint separation. Joints will be inevitable, but no separation horizontal nor vertical, no misalignment. The slab should have adequate stiffness so that under the concentrated load of a truck will not crack, or if it does crack, it is within acceptable limit. Now, the image we have on the left is not acceptable for the type of industrial slab we are discussing today. You see the crack formation very obvious. Image on the right is an example where you have a smooth and level surface. Now, construction options. What are construction options? One is conventionally reinforced concrete or post-tensioned slab on grade. You can have an industrial slab constructed with concrete and steel fibers for reinforcement. Slab reinforced with combination of steel fibers and post-tensioning. All require the same type of soil support in soil evaluation and preparation. Now, let us concentrate a second on the soil support. The finished surface obviously has to be smooth and level. It must have limited instantaneous deformation under concentrated load of forklift. Stiffness, it has to have enough stiffness there. And long term, it should have management settlement under sustained loads, such as load from the stacks. Now, it must have low friction between itself and the slab. This is something which comes more clear as we move along the presentation, the low friction. The low friction between the slab and ground. So instantaneous deformation depends, apart from the slab itself, on the soil below the slab. And the soil below the slab, its instantaneous deformation uses the bulk modulus of the soil. That is a constant property of the soil, expressed typically in newtons per millimeter cubed or pounds per cubic inch. A well-compacted engineered soil foundation will have a bulk modulus of about 0.12 Newton per millimeter cubed, which is approximately 400 pounds per cubic inch. Next is the friction. That is very important between the slab and the soil support. It has major impact in the economy of design and its performance, as it will be clarified in the following slides. Impact of friction on design and performance will be discussed shortly. Friction between the soil and slab can vary between 1, which is very, very high, to 0.25, which is probably the best you can do, rarely achievable. It is tough to achieve 0.25 friction coefficient. Now, putting two layers of 0.2 to 0.4 millimeter sheet of plastic will reduce the friction coefficient to something of the order of 0.35. That probably will be the target of your design. Most designs, at least the ones we've come across to, have been designed for friction coefficient 0.35. Now, what about the loads? Self-weight obviously is small relative to other loads. It's directly transferred to the soil, does not play a significant role in design. It doesn't govern the design. Now, uniformly distributed load placed directly on the floor is distributed. Again, this is something which does not govern the design. The magnitude of it compared to the allowable soil pressure is pretty low. Forklift and rack loads, where the material is stored, these are concentrated loads from the leg of the racks. These could be high. They can govern the design. Forklift tires can also govern your design. So essentially we concentrate on the load from the racks and from forklift. This slide shows one configuration of loads and magnitude of the loads. This is one, but obviously each will be different. This is just an example. And when it comes to wheel loads, again, this is one configuration which represents a forklift. Depending on the forklift used, the configuration and the concentrated load will be different. Now let us concentrate. What is your design target? Your design target is to limit the crack formation under the load to an amount that does not impair the performance of the floor. We are not talking about initiation cracking at a point. No. We are going to talk about cracking extending in an amount which will impair the design requirements. Under the load from above, you have a distribution of soil below. And this distribution and load from above will result in bending moment and stresses in the slab. Tension stresses develop at slab soffit from application of the load. High tensile stresses obviously initiate cracking at a point. Now, cracking reduces the slab stiffness, but cracking must extend to a minimum length before its impact becomes design significant. Cracking at a point does not matter as far as performance is concerned, but it has to be long enough to influence the stiffness by an amount which will have negative impact on the performance. For this reason, very much like the elevated slab where you have design strips for design, for this reason, a design section or a design width is defined. If you have a concentrated load, there is a width which is concentrated load plus 1.5 times the slab thickness on each side. This is the design width. And if you have more than one, this will be the design width. What does this mean? We will use the actions on the design width and try to determine whether cracking over this length is likely to occur or how much it is likely to be, and whether it is going to impair the performance based on our design criteria. Now, design width is defined as the extent over which the representative stress reaches the value that is associated with design significant cracking. Design width is function of dimension of the load and slab thickness. Dimension of the load and slab thickness define the design width. Now, what is the stress that will be driving our design? This is what I call here computed design stress. Now, if this is the design width and here is the distribution of action, this distribution, this moment is integrated, so you have a single total moment associated with this. And for this total moment acting over this section, you will be calculating a design stress. Stress is moment divided by section modulus plus precompression if it is pre-stressed. In our case, we are dealing with post-tension slab, so in our case we will have moment divided by section modulus plus FPC, which is precompression. Now, the allowable stress which we target is the cracking stress over a factor of safety. The cracking stress of the concrete is defined by this value in ACI. EC2 has a similar value, and it is a function of slab's 28-day compressive strength. We calculate the cracking stress divided by a factor of safety, and that will be our design target. Now, what are the construction options? The options are conventionally reinforced, post-tensioned, or slab with fiber reinforcement, or combination of fiber and post-tensioning. The question that I want to raise now is why post-tensioning? Why? When simpler options may exist. So I like to draw your attention a little bit on cracking and shrinkage. Here, if you have slab supported on ground and it is not post-tensioned, shrinkage will result in cracking. And the remedy is typically to put rebar, enough rebar which will go across the crack, and it will develop, rebar obviously will develop tension, and the tension in rebar will be transferred to friction between the slab and the ground. That is how it is handled if there is no post-tensioning. Now, how much cracking are we going to have? Typically, concrete cracks at 500 microstrain. or let me put it this way, concrete shrinks about 500 microstrain. That is 500 times 10 to the power minus 6. 500 is good actually. Most concrete in construction is more than 500 microstrain. It goes up to 700 microstrain. Now, concrete material of 4.35 KSI concrete or 30 megapascal cracks in tension at 125 microstrain. Now, what I want to draw your attention to is that concrete shrinks 500, 500, but it cracks at 225. So it is obvious that concrete is going to crack if you do not undertake a measure to control its cracking, because the shrinkage value is at least 4 or 5 times than the strain which causes cracking. So unless slab is allowed to shorten over its entire length, it cracks. So one option is to put rebar. The other option is to put the slab on rollers. If you put it on rollers, or if you allow it to move, obviously it will shrink and it will not crack. Shrinkage is many times larger than cracking strain. Here I have another presentation. I show you the amount of total shortening, how much of it is due to shrinkage, and which is 500 microstrain. But if you put pre-compression, which is commonly done in ground supported slabs, you only apply 25 microstrain. Now here, pause for a second. Pause and look at this. Post-tensioning will result in pre-compression. Pre-compression will shorten the member. How much is it going to shorten? For the values that we use in industry, only 25 microstrain. But concrete is going to shrink 500 microstrain. So how can it prevent cracking? The only way it can prevent is if the slab is on rollers. And when you apply post-tensioning, the post-tensioning pushes the ends of the slab toward one another, and the slab on rollers will compress. That brings us to the critical question of designing industrial slabs, that you have to allow the slab to shorten. Your target should be a very, very small friction. We cannot eliminate friction, but we have to reduce it to an amount that under normal pre-compression, the slab will move, will slide. That is the target. Post-tensioning targets to overcome the friction between the slab and the ground supported. Now we are concentrating on post-tensioning contribution. The diagram here just shows that if you have a load on the slab, this is the distribution of pressure, and the distribution of moment is something like that. You have compression at the top, you have tension at the bottom, and typically tension and compression are used the same. But if you apply pre-compression, the pre-compression reduces the tension at the bottom. So here at the bottom, the value is smaller than the one at the top, and it delays the likelihood of cracking. For a long slab, remember, tendons lose their force along the length, not only from friction, because that's a different issue. Loss in tendon force has nothing to do with friction. It is loss in force because of friction between the tendon and its sheathing, not between the slab and the ground. Tendon encased in a sheathing, when pulled, it loses some of its force. And here is the force you lose at anchoring the tendon. So the distribution of force in tendon is what I am showing here, on the assumption that the tendon is stressed at both ends. So here in between you have the low point. The purpose of this diagram is to emphasize that your design will be based on the stress situation at this location where the contribution of post-tensioning is least. In construction, the slab is subdivided to optimize the distance L0, to optimize this distance. By subdivided, I mean the total length is broken into pieces and stressed along the pieces so that you will reduce this length. That is to reduce loss in pre-stressing from friction between the slab and its support. Now, a comment on the pre-compression. And the comment is that in your design, assume that the pre-compression is uniform as shown here on the slab. Uniform here, irrespective of whether the tendon for any reason, by installation, by mistake or whatever, is below the neutral axis or above the neutral axis. In a freestanding member, the tendon has to be at the centroid to give you uniform precompression, but not in the case of ground-supported slab. In this case, if the tendon is below or the tendon is above the neutral axis, there will be an initial short distance over which the soil pressure will be adjusted such that the outcome away from the point of application, the distribution will be uniform. So for your design, assume uniform distribution. This is described in a reference that is given in the book, the proof of it. It says, irrespective of whether the tendons are positioned below or above the mid-depth of the slab, the outcome of the post-tensioning is uniform precompression at distances away from the anchorage. The impact of anchor location with respect to the slab's centroid is limited to a short distance in the vicinity. So let us go back again and review the post-tensioning and load from the top and calculate the design stress. Here, purposely, I have shown the tendon below the neutral axis, but I have considered its contribution as uniform precompression, and load above and pressure of soil below gives us this. These are the two distributions that we will be dealing with: soil pressure and bending moment. Now, this pre-compression is uniform. That is what I have considered. Good. This is something which we discussed. In this case, good. Let us go to design steps. The first step is the soil property. And the soil properties, when well done, well prepared, is a target of about 400 pounds per cubic inch for its bulk modulus, or this amount in SI. Then you decide on the material to be placed on top of the soil, typically 2 layers of 0.01 inch plastic. And in some instances, I've come across that the contractor puts or sprays a lubricant between the 2 layers so that the 2 layers can slide over one another more readily. You target a friction coefficient between the slab and the soil of the order of 0.35. And then you go to loads. The loads are given by the configuration and contact area of the stack or the truck. You need to know the magnitude. You need to know the area over which they act. You put a impact factor 1.1, 10% if you have a forklift, not for load frames. And then you decide on a safety factor, and typically 1.5 is assumed the safety factor for cracking. You define your concrete strength, and then you start with an assumed slab thickness, typically 4.5 to 7 inches. And then you define your allowable stress, which is the cracking stress divided by factor of safety. And you define the design width, which depends on the dimension of the load and the slab thickness. And you calculate the design stress. You compare the stress with the allowable value to determine whether you have to increase pre-compression or you have to change concrete strength or otherwise. We will go through a numerical example toward the end of this session. If in your first estimate the pre-compression needed for the factor of safety you assume ends up to be more than 0.8 megapascal, more than 100 psi, then you have to increase the slab thickness for economy. It means the slab thickness you have assumed is too little, or the concrete strength is too little. If the pre-compression required by your calculation is less than this value, then you reduce the slab thickness. The slab thickness you have assumed can economically be reduced. Now, in our design steps, we select the post-tensioning system. By that I mean bonded or unbonded. We select pre-stressing parameters, divide the slab into pore segments, determine the effective force per tendon. Now, after you subdivide the slab into segments and you have already decided on your pre-stressing, then you can calculate how much is the effective force at the far end of the tendon, because that is where you will do your design. For the stressing segment length, assume now that comes in the next slide. For the stressing segment length assumed above, determine the long-term residual force per tendon. This is segment assumed above. We had here determine the effective stress and break the slab into segments. We will go through this in a numerical example shortly. So use the friction loss between the slab and the tendon over the segment length that you stress. Determine the loss of force due to friction. This friction is between the slab and the ground, not between the tendon and its sheathing. That is different. Then determine what should be the spacing between tendons such that the difference between effective force in tendon and loss in friction will provide you the precompression you need. Then you detail for construction. Here I have an example. On the left, the slab is being cast, and on the right, it is prepared and ready to be cast. Another example where slab is subdivided into pores for stressing segments. This is another segment, this is another segment which will be stressed afterwards after this is stressed. On the left you have an example under preparation, ready to receive concrete. On the right is the finished example. Now let us talk a little bit about construction detailing. The objective of the construction detailing is to determine the amount and arrangement and stressing of post-tensioning in order to meet your design target. Design target is computed stress to be within the value you assumed. At design stage, the required precompression is determined. You calculate how much precompression you need at the far end of the tendon. Then you break the floor into segments of either stressed at one end or stressed at two ends, and typically the segments will be 30 to 50 meter long, 100 to 150 feet, or if stressed at both ends will be more than that, will be twice. Select the post-tensioning system, unbonded or bonded, and then you know the strand area, you know the stressing, you can calculate the losses and find the final effective stress that you use for design. You use the final effective stress and the required precompression to determine the number and spacing of tendons. Again, here I have another example of having subdivided the slab into segments for casting and stressing, and one which is ready to receive a concrete. Tendons are typically supported at intersection in detailing, and if you have obstructions to shortening like columns and walls, you have to provide them, wrap them with compressive material which will allow the slab to shorten without obstruction. Detail of stressing end for the slabs constructed in the US are very simple. 2 number 4 bars behind the anchor. That is all you need. But in other places, it is common to put more, or even come up with a spiral, as I have shown here, or this type of closed dowel. Now let us apply what we discussed in a design example. It will illustrate the points we went through. It says, design the industrial slab for the storage facility shown below. This is the dimension, and this is the arrangement of the loads from forklift, the geometry, and the magnitude of the load. In this design example, soil properties given by bulk modulus. We assume 2 layers of plastic over the soil. Assume coefficient of friction 0.35. We define the loads 6 tons on each leg, each point of contact. Point area of contact defined. We put 10% impact, add 10% impact, and select a factor of safety of 1.5. And we select this concrete strength. For this concrete strength, the modulus of elasticity is so much given in the code, depending on the code you use. This is based on ACI. Now, we start with slab thickness of 7.1 inches, 180 mm, and see whether it works or not. If it doesn't work, then we would increase it or decrease it. Then step number 8, calculate the allowable design stress. Now the design stress is the cracking stress, which is property of the concrete. This is the cracking stress divided by the factor of safety. So this is my design stress, cracking stress divided by factor of safety. Then we use a software which is based on plate on elastic medium. Define the design parameters and we obtain solution. Solution typically gives you a contour of soil pressure and gives you a contour of bending moment and so on. Here is a contour of soil pressure. I have shown it for interest. How much, so that you see what is the maximum pressure at a point. Obviously, pressure at a point doesn't mean anything for design. You have to find the pressure over the design section to be of significant influence in your design. Good. Then the software will give you the distribution of moment in one direction, mxx. Again, the contour values. These are just for visual. When the time comes to design, we need the bending moment over the design section. This is distribution of moment in the other direction for the parameters that I defined using one of the commercially available software. Next, after I have the solution from the computer, I go back to the loads, configuration of the loads, and calculate the design width for, in this case I have 2 loads, so the design width will be a little bit larger than there. So the design width in one direction is this value here, which is based on this calculation. It is 980 mm, and in the other direction will be different. Now, then I come and consider the loads, and this is the design width in one direction, this is the design width in the other direction. I note the distribution of moment over the design width in one direction, distribution of moment over the design width in the other direction, and for each distribution I calculate the area, which is the total moment. Again, commercially available software, once you have the design width, already calculates the integral of the moment. You don't have to do it manually. And these are the integrals are given by these values for the example that I gave you. Then the design stress is the integral of the moment over the bulk modulus of the design section. This is the value of the bulk modulus for this length, and the stress calculated is so much. I compare the calculated stress with the allowable stress, which I had before. The allowable was cracking divided by factor of safety. So this is the cracking divided by factor of safety. This is allowable, 2.28. Calculated 3.02. So it doesn't work. I have to put pre-compression to reduce this calculated stress to be not more than the allowable. So this is where the pre-compression comes into the picture. The pre-compression needed is to provide stress for the difference of calculated and required. So pre-compression needed is the difference between the two, and this is 0.74 megapascal. Good. In order to continue with the design, I need to come up with the detailing to know what is the tendon length, so that I can calculate the force at the far end and make sure that the force at the far end gives me the pre-compression required. So I break down the slab into this configuration for stressing. The corner here could be stressed at both ends, but the others can be stressed at one end. This also stressed at both ends, but this one at one end. So I select unbonded system, use 1/2 inch strand, and the friction between the strand and its sheathing is this value. So I can calculate friction loss of the strand, which is between the strand and its sheathing, not the soil. Stress it at 0.8 times the ultimate, and there will be a seating loss at stressing when the tendon is anchored. The slab is subdivided into these sections, and the length is about 40 meters here. This is the formula for friction loss calculation. I find out that at the far end, the force will be this fraction of the jacking force, 0.85, because of friction at the far end. And that is really I have to use at this far end, 0.85 of the jacking force. And 0.85 of the jacking force gives me so much force at the far end, which I can use for design. So let me see whether I can move this out of the way. Is there a way? Maybe here would be better. Good. This is the subdivision. Good. Didn't like it. Okay. Didn't like it. Let me put it back. Didn't work well. So we determine the minimum effective force along the tendon. That means for this here, the minimum force will be at the far end. Let me see whether I can park this somewhere. Maybe here. Okay. In order to find the minimum force, I need to know how much is the long-term loss. Long-term loss, I have assumed 80 megapascal. So the effective, this is the effective long-term loss. Friction coefficient, I have assumed 0.35. So I have the force here. I have allowed for some long-term loss. I have the friction between the slab and the ground. So I should be able to find the tendon force at the very end. So loss of force for 1 square meter friction will be, this is the weight, slab thickness, density times friction. So I am going to lose this amount of force per unit area of contact. And the area of contact I have is 40 feet here, or 40 meters, times this value loss per unit area. So at the far end, there is so much loss due to friction between the slab and the ground. So force required at the far end is this amount, which is by design, plus this amount that I lose to friction. So I add to whatever was required by design the amount that is lost by friction. So that must be the force I need to have at the stressing end. And this, if each tendon gives me this much force, and this is as much as I need, so the spacing of tendons should be this much. So I put 2 strands every such spacing. Now, finally, that brings me to the conclusion as far as design example is concerned, because the objective of the design example was to find out how many strands I need at what spacing. This is just a comment that if you are not sure how to get the friction coefficient for the type of condition you have, you select this board, you put the overlay plastic as you want to use in the job site, and lubricant in between if you want to use, and you use a concrete sample with the thickness that you would be using for the slab, and you gradually raise the end until this block starts to sliding. Your coefficient of friction will be A divided by B. Now, summary. Thank you for listening so far. In summary, I talked about different types of ground-supported slab: mat foundation, slab on expansive soil, industrial slab, construction options, conventional RC, post-tension, steel fibers, but we concentrated on post-tensioning. Why we use post-tensioning? Because post-tensioning can move the ends of the slab toward one another to close the shrinkage cracks which are inevitable. Post-tensioning best handles the friction. That is the reason. We talked about tendon layout, could be at the centroid typically. We went over design steps and detailing steps and went through a design example and concluded by how you can determine the friction coefficient of the structure you have. The information presented to you was extracted from one of the chapters of this book. Thank you for listening.